Hi everyone, welcome back to our YouTube channel, Becoming a ROS Developer. So today we've got Salvador, who has completed the course ROS 2 Basics in 5 days using Python. So he'll be giving us a presentation about his project and how he has managed to get it accomplished. First of all, we'll see a demonstration on the real robot, and then after that, we'll get into the details about how he solved the problem. So I'll now hand over the floor to him. Over to you, Salvador, whenever you're ready.
Hi, how are you? My name is Salvador. Okay, so in this project, I have a few slides that you can use to show.
All
Great.
right.
So in summary,
Have you connected
the project is that there's...
have you connected to the real robot yet? Not yet. Just... Okay.
Connecting now.
All right, yeah. I think you should do the demonstration first, and then you can get into the slides later on. Is that
Okay.
correct?
Okay, sounds good.
Okay, good. All right, can you be explaining what you'll be doing there?
What I'm doing in the terminal?
Yes, it's ideal that
Oh, gotcha. So yeah, I'm just doing some setting up, getting the programs ready to work. I'm sure you've noticed that I did this install, and I will go over why I did that in my my presentation.
Okay.
But let's do this demo. Yeah. It just gets you nice in a good starting position, and then just find some random orientation.
All right.
That'll do. Great. So. Okay, so this is going to start up the several nodes, which are going to perform. Let's try it again. Oh no. Okay, there we go. I think there was a non-error there.
All right.
So we start out, we call this service, which is going to find the wall, approach it, and then orient to prepare for wall following. When that's ready, we have wall following logic in our main script, which is going to also call another node with the action, which is recording odometry. And this odometry will have a record of our positions, as well as a feedback of how far we've traveled.
Okay.
Just a little bit nicer. And if I'll narrate just a little bit about what's going on, the decisions that the robot's making,
yes.
There are basically two categories of the wall following behavior, which is normal and corner actions.
All right.
The corner actions start when the front laser range, which is just a mean of a few of the indexes, when it registers that there's an obstacle in front, I have a predefined curve, something that I experimentally determined was an appropriate curve path to follow. And then once it exits that, it will return to this, what is the wall following behavior.
Okay.
The wall following behavior is a combination feed forward proportional controller.
Okay.
which maybe I made more convoluted than it had to be, but this was a lot of fun that I got to, practically apply my controls knowledge.
Right,
I
right.
definitely have I definitely have the theoretical background in the controls part. And then if we're correct here, oh, that's unfortunate. So actually, the demonstration just failed. What was supposed to happen is that the robot at this point should have been within the threshold.
To stop.
Um, but I guess accumulated error, prevented that. So
Mm-hmm.
let's see if we can correct it with another run. And I will resume my explanation, my narration of the behaviors that the wall following is doing.
Yes.
So this combination feed-forward controller has a nominal state, which is just, I think, a fancy way of saying that I have ideal behavior that I'd like to follow.
Right.
And that ideal behavior is that I'm going forward at some velocity
Yes.
and that I have no angular commands.
Right.
What I do is I take the magnitude of any type of error, an error, let me define that real quick before I get ahead of myself.
Mm-hmm.
I have a distance error, which is the distance between this 0.3 meters that I want to be at
Mm-hmm.
versus where the right laser is reading. And then I also have an angular index error, which is calculated based off of the index of the nearest laser reading
Mm-hmm.
and the defined index of the right of the robot. So in this particular case, this is a 180. Oh no, that's not good. Again, very nice demonstration of the real world components of
Right.
robotics programming
Right.
is that a lot of things go right and a lot of things go wrong.
True.
And
Yeah.
sometimes it's luck. And this is precisely why we do controls, right?
Yeah.
Because we can't perfectly prescribe motion as well as we try.
Mm-hmm. Yes.
Sometimes I suspect is that uh, there is a jump in reading, and this causes the command to make it rotate in such a way
Right. Right.
that it will register in front that there's an obstacle, and that triggers the corner behavior
Right. I see.
because it's not like
It's
So
it's a very interesting thing. Because I was also thinking it's probably because it all of a sudden registered that the 180 degrees out is now its front, right? When it does the laser scan. We had a similar problem earlier on, but you can go on.
continue, please. What were you saying?
I was saying,
You're saying that another
yeah, it's
presenter had a similar situation.
it's not with the robot, it's just the way we process laser scan data, right? Like for example in your code, right? If you don't handle the case where it mistakes your index is the 180 degrees off, right? That's the rear instead of the front, right?
Yes,
Yes.
exactly.
Yeah.
Yes, it registers for a moment that this is the closest object, and therefore I define that as wall.
Right. Right.
And then and you can have some pretty big control commands come in,
Yeah.
and then that has some error.
Mm-hmm. So it's very important to handle that swap from positive 180 to negative 180, something like that, in the laser scan readings. Yeah. But go ahead.
So let's see. What was I speaking about specifically when that happened?
It was just a second demonstration to see if it could exhibit some of the behaviors you're talking about. But I think let's get into the slides now, because
Sure.
I think your demonstration was very enlightening as well.
Okay, so in summary, the project is we need to follow this wall at some desired distance.
Mm-hmm.
And the tools we have are some odometry data, some laser scan data, and we prescribe motion to this command topic.
Yes.
And we also have some requirements about the approach. We have a service which is going to set up for wall following. We have an action which performs some record collecting of odometry.
Mm-hmm.
And then we have the main meat and potatoes, which has all of the references, the calls, and the wall following logic itself.
All right.
So some comments about my approach. When I was taking the course, this was used for calculating, yaw calculations. We use this package TF transformation, but for some reason this doesn't work. And despite attempts to install, at least on Foxy or whatever this virtual computer is doing,
Right.
it was not working. So instead, I found an alternative which works just fine, and it's transforms 3D. So if you saw at the beginning, I definitely have to do that whenever I restart the terminals. So,
Okay.
secondly, the simulation has different positioning on the indexes of the laser.
Right.
So we start in the front at 0 and around 719, but in the real robot, the front is at this 360.
Right.
So there's some differences in the logic that have to be accounted for, but I've done my best to separate that out to make it as easy as it can be to change between simulation and real robot. The ultimate logic of the wall following, it's an overview. We can look into the more technical details shortly. But I am looking specifically from the laser data to get my front distance reading, my right distance reading, the nearest distance, and the index of the nearest distance. And then I have a timer which calls this manager function, which is basically checking some statuses. And if all is good, then we're performing wall following.
Right.
It begins with calculating error, and this is one of those things that has to be adjusted based off of the real or simulation. So this calculation, and then we do an evaluation for what type of logic we're going to do. If we're within some threshold, if the wall is further away, then we do this nice normal code, which is the wall following logic that I've tried to explain. And then if the wall is close enough, well, then we do this predefined curve.
Right.
So this is the feed-forward controller I was talking about. I have this nominal state, which is the max speed that I'd like to move at, which is 0.06 for linear direction. And depending on some function of and I'll go into what that function is, but depending on what that function is for depending on the size of this error squared, right? I keep clicking. Then I will have a reduction in linear speed. And the reason I chose to do this is because when we're moving quickly and errors arise, either from miscommunications or whatever happens, if we're moving fast, then those errors can accumulate really fast.
Really quickly, yes.
They are amplified, I guess is the word I might use. So whenever there's any kind of situation that's not great, I just have it slow down so that the angle control can correct things. And the angle control does it's a weighted minimization of the distance error and the angle error, depending on different situations for which is prioritized. And then I also have this integrated component here, which I can't show because I can't show this integrated component of the wall distance here, because I had this issue where I would make the curve, but it would not actually stay at that 0.3 meters distance from the wall that I wanted. So it does this calculation, and then I have a check here to make sure that there's no way that we accidentally go backwards. So if this guy here is greater than the max speed that I've chosen, this would make it negative. So I have this special don't go below 0 because sometimes it'll just go back and forth if we do that.
Yeah, very nice. Very nice card there.
Yes. And then ultimately those commands get published to Twist on this CMD val topic, and then I sleep. The reason I sleep is to prevent some chattering. There is this balance in the stability of the controller.
Yeah.
The real robot needs a little bit of time to respond and actually do commands rather than just think about it the whole time.
Yeah.
And so this small sleep was my solution. It's a band-aid solution. It's not eloquent, but that's robotics engineering.
Right. I'm quite curious. How did you choose the amount of time it was going to sleep?
I do my tuning based off of magnitudes. So I start with really low values, and then I come up and I find the range that's like, okay, this is stable, this is not stable.
Right.
And then within that range, I okay, I'll increase it a little bit. I'll decrease it. It's kind of like Nyquist.
I see, I see.
Yeah, in some ways. Find where it's unstable and then try to stabilize it.
It's a good thing that
Um,
there's some intuition to always start with the smallest ones, right? If that wasn't there, then it would be very difficult to tell whether it'll be the greatest values or the smallest values that will give you that stability, you know.
okay, so you're saying you give a suggestion for me to start at lower values,
No, no, no.
lower magnitudes.
No, I'm saying it's a nice thing to have that intuition to know, right? In these cases, it's almost obvious
Oh,
that if you start with the lower values, yeah, you're bound to be in the safe zone. Whereas with some cases, you don't know whether you want to start with the big ones or the small ones.
mm,
Yeah.
yeah. Some of these things hard to communicate with people who don't have that experience, and I find I think I would consider myself in that in between,
Right.
where I'm aware of certain things, but not fully to the extent of, oh, I immediately know the solution. And that's what makes this fun. That's why I'm really enjoying this, is because it's like, okay, I can figure this out. I can do this.
Right. If
Okay.
close,
Uh-huh.
close, you feel that you're close. Yeah,
Exactly. It's you can taste it.
it's wonderful.
Okay, so that's the wall following part. The service for finding the wall involves these three components.
Mm-hmm.
So I have this timer, which is constantly calling this preparation method at 10 hertz.
Right.
And this does a check. This checks if I have this status flag that's true. And if it's not true, then I'll just end and I'll just return. The only way that this is evaluated as true is when we get a call. This call immediately sets this guy as true and returns the status. You'll probably ask me, well, why am I returning a status before I do anything?
Mm-hmm.
And I chose to make this service something that could be called multiple times without interfering the other things from running.
I see. I
Uh,
see.
so, yes, again, with what works rather than what's perfect.
It's always
I
the
will
best.
go with working before perfect.
That's engineering, right? Yeah, it's always the best.
Yeah, exactly,
Yeah.
exactly. There's the academic theoretical setting, and then there's the this is the real world, and
Right. The
so.
engineering bit, yeah.
Mhm. I'll when I return to the wall following part, I will explain how I choose or how I prevent this from interfering. And it's just a call. It's just a checking.
Okay.
And until that check is satisfied, we are not doing anything.
Right. Right.
Okay, so I've gone on that. So we have this in preparation. We have these steps. When we initialize the node, we start at step is equal to 1, and we perform each of these are a method that I've defined, and based off of the number, that method will be executed.
Okay.
And what it does is it has a specific error calculation, and I minimize that particular error to some threshold. So, for example, the angle index error I have to like 5 degrees or 5 units, which I think is maybe like 2.5 degrees in the. So if we're within 2.5 degrees of where I want to be, then okay, good enough.
Mm-hmm.
Otherwise, the robot, because of noise, because of real world complications, it might never settle.
All right. All right.
Uh, so it iterates through these. So this is going to find the wall, and then this is going to approach the wall, and then this is going to prepare. This is going to orient to have the right towards the wall. And then once this is all checked, then I have everything stop moving. Let the inertia of the robot settle. Let everything just be calm. And then I set my statuses as okay, I found the wall, and turn off preparation
Okay.
so that we're not, doing more calculations and stuff in the background.
I see. I see.
The action itself, very similar in, or not too complicated, I think, in the way that I approach this. Maybe there are better ways, but again, if there's anything that we've seen about this presentation is that we all approach this in our own way.
Yeah.
So,
Yeah.
So we receive a call. And I have this, I initialize everything. Well, okay, so the constructor has a lot of the main variables and statuses initialized. But when I say initialize, I mean, okay, I reset my distance to 0.
Mm-hmm.
I record my first odometry based off of whatever. This guy I made re-entrant. So as soon as this node is turned on, this guy's running and this is populated.
All right.
And then as soon as I get the call, I pull this guy, set that as my first odometry.
Okay.
And then I turn on my status for the recorder. I set that as true.
Right.
And then I have a loop because I want to prevent this from returning until the action is complete, which is the one lap around the wall.
I see. Yes.
I have this loop while true. This is how you see the sleep here. This is how I get it to run at approximately 1 hertz. And then this recorder logic I've actually put over here in this pink block to better see the decisions and the process that's going through.
All right. All right.
And what happens is, while true, I'm going to add this guy with the newest reading of where I am to this list of where I was. I do a calculation of how much I moved between where I was last and where I am now.
You got 5 more minutes.
This is Euclidean distance. 5 more minutes? Okay.
Yeah,
I will pick this up. Thank you. Okay, so I find the distance of where I was. One more time.
You should get to just show us your scripts as you just finish up.
Gotcha. Okay.
Sure.
And then this is the whole interaction, blah, 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 blah. And then this is what I was able to get in the simulation. And you could see I was experimenting with different parameters and what the physical relationship of what these things meant. Like this orientation starting in this way was something with the threshold. So maybe if I lower it or, okay, so now we can look at the scripts themselves.
All right.
You can see a lot of testing that I did.
Yeah, I see.
Okay, so this is the action server. You can see, some vestigial code. Have all of my imports. This guy, which is different from TF transforms. I create my reentrant group, create the subscription to the odometry. I create the action server. This guy here, this callback is gonna refer to over here. This is where all the meat and potatoes is. I make my status flags. I set up my variables. And then here, in the odom, what I do is I create this point variable, and then I assign it values based off of what we're reading from last odom. And then I set my calculation. I do the calculation, and then I set that as the guy. So boom, 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 boom. We're getting this message is currently updated.
Okay.
Here, create another point variable. This is first odom. Assign those values. Over here, I create the gold candle. I'm going to need this for doing accepted or not.
Okay.
Create the empty array. Set as true. And then while true, I create this temporary point. This was something that was unintuitive to me, is that what I tried to do was I tried to just add last odom. I tried to append it directly into the record.
Yes.
But there was some reference interaction that was kind of strange. And how it was explained to me is that by doing that, I would constantly overwrite every variable in the record. So what I instead is I have this just stepping stone point, which I use to put in. This is updated based off of the last odom. And then this gets added without overriding everything in the record.
All right.
Then I calculate this distance. So this is last and current. And then I add on the total distance. I add this on to the total distance. Great. Then this is where I do feedback, create the feedback variable, set it as this, publish so that I can see it in the terminal. And then here I send it to the action topic. And then this is here. This is to prepare for the next loop. I update the previous position to the current position, and then I do an evaluation of my end condition. And the way that I chose to do this was if the length of the record was greater than 10, so in theory, at least 10 seconds, and then the distance was in this, 0.05. This is my way of making sure that we weren't going to immediately return as true once we started. And then here's that sleep for 1 hertz, or to get it to happen at 1 hertz.
I see.
And then finally, once this evaluates as false, and when this is true and this evaluates as false, then we exit the loop, create the result variable, assign the value, define success, and then, oh no, and then, return.
All right.
The service, uh
I think yeah, it's all right. It's a wonderful presentation. It's a wonderful presentation. Really like the way you did it. It shows that you've got a very strong background in controls. So very nice. Um, I would like to ask you a couple of questions though. At the very beginning, you realized that your robot returned not a number, right? None at the very beginning.
yes,
And
and I think that was because I was trying to do something before I had a value assigned.
Right, right. How could you have dealt with that, for example, right? I had one case where,
I could put a check.
right?
I'm sorry, I keep interrupting you.
No, it's fine, it's fine. I was just trying to probe the idea of putting a guard for something like that, for example, because let's say you get not a number on your laser readings, right? Instead of your system crashing, there should be some handling. So I was trying to find out how could you have dealt with that.
Yes, so what I could have done is I can put a check to see if the data has been written yet. So if we establish everything in the constructor as none, then this is a good way of letting us know that things haven't been done yet.
Yes.
And then if we try to access it, what I can do is I can just put this if check. And if it's like, oh, if this guy's none, if this guy's none, if this guy's none, hold off a minute,
Right.
just stop, and then the node will spin again, and all of these things, all of these callbacks will update, and then now the value should be assigned, at least in theory.
Yes, yes, okay. At least in theory, yeah. The other thing I wanted to ask you about is you spoke about using corner actions, right? So it's almost like you put a separate control measure for all the turning that your robot will do, right? Can you give us a little bit more background behind that? Why did you choose to separate that control algorithm from the general wall follower? Because I think it will still turn when it realizes that the threshold is below 0.3, right?
Yeah, so this is something that I put in place because when I didn't have it, what would happen was that I would approach very close to the front wall. So if this is, I'm here at this, I don't know if you can see my camera. I'm here at this wall.
Yeah, I can see. Yeah.
And I'm going, and then I approach the front, and I'm going to hit. What would happen is that the arrow evaluations would change very quickly, and it would stop moving, and then it would have a dramatic increase in the angle turn.
All right, so it was like hard stop, more or less.
It was an aggressive command, and when I tried to like make it calmer, then I found that the rest of the wall following behavior itself wouldn't respond as well.
Okay, it would be out of.
So,
yeah, I see.
So I think ultimately that's a problem that arose from my approach to how I chose to do this. I think maybe if I had a bit more involved with using pose and such, then I could do some more, I guess, independent.
Yeah,
but
yeah, I think
since my background is in controls, I really wanted to make this be able to avoid.
I think the way you did it is quite nice. It's just if you consider the cut and dry way of doing it, right? You would let it approach, get to at least 0.3, and then you make it stop, then you make it rotate, right? But you were trying to smoothen it out. So I really admire that you were trying to make that effort to make it smoother. So I wanted to understand what led you to that. So well done, you have explained the reasons behind it. Then the other question I wanted to ask you is, you spoke about accumulated error, right? So you said it's missed the beginning at the very, it went for the second round, right? Almost for the second level. What do you think might have caused that, right? What do you think might have caused it to miss the original beginning, for it to notice that it
Great question.
completed the loop? Yeah.
I've thought a lot about this, and I think it has to do within this threshold of, I guess I'm going to say, Can you hear me?
Yeah, I can hear you.
My screen has gone black. I don't know if that's from me or.
I think that was from you, but now it's back. Don't worry.
Okay. So I think that the reason this happens is from this little threshold of luck. And what I mean by that is when and where the robot starts uh, and it starts and exits this corner behavior. So if we look here, we start here and we do this, and this guy looks pretty nice. It looks
Right.
pretty. I won't lie. It's nice. But if we look over here, we see it's a little different. It starts early, and that means that it's going to exit out of corner action,
A lot
which is
later.
like when it's like it's gonna exit out earlier, and then the regular logic will dominate, and that has some relatively large effects because we're exiting at an angle relative to the wall that we don't want to be.
Okay. Okay.
And so we have this like what happens, you see this dip, this overshoot and correct.
Yes.
Um, this is as a result of the angle that we exit out of the corner action.
All right. All
I've
right.
tried to make the corner action more aggressive. Like I've tried to make it the linear component slower so that it does like a toot 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 and we come out. But ultimately, so long as that we're not reading corner action, then we're going to alternate between predefined curve and the feedback control loop.
Okay, I see. So, my assumption is that you were using some type of distance marker, right, to check the whether the robot has reached the end or not. Is that right?
Uh-huh.
Right. So, based on how the loop or the oval is drawn, or how it goes around the circuit, your values will change. Your original odometry readings will either be slightly bigger or slightly smaller. Is that what you're saying?
Can you repeat your question? I don't think I understood correctly.
So I'm saying from your explanation, are you saying that based on how it goes around the circuit, your odometry values will either be slightly bigger or slightly smaller, um, in terms of the exact distance it is traveled?
Are you saying the distance in between? And so when it registers again, it might have skipped over?
Um, well, not really,
I
but
don't think that that was the problem.
right, right, I
It
see.
might be, but I don't think that that was the problem.
All
To
right,
me, it was the correction of this error, this distance error, before we approached where we were. What
all
happens
right,
is
I
that
see.
we leave corner actions maybe around here, which gives us however many seconds here to appropriately correct.
Oh, okay,
Um,
okay, there we go. Now I see what you mean. I see. All right.
gotcha. I guess my explanation was
It's all right. It's all right. Very nice presentation, Salvador. I think we'll end it here. So just hang on.
okay.
We'll finish our conversation on. So, all right,
Okay,
everyone.
thank you. I appreciate it.
Sure, sure. All right. So this was Salvador's presentation, and I would like to congratulate him for a very job well done. Very intriguing approach to this project, and we highly encourage all those who would want to try any of the courses that we offer certification on to give it a shot. And if you have your own way of implementing the same project, go for it. We wish you the best. So until next time, keep pushing your